Okay, we stopped here yesterday, so might as well continue. So we discussed what is a Turing machine, and we have a basic definition, and we constructed many different Turing machines, like one that copies, one that adds one. Then we discussed what does it mean to concatenate Turing machines, and we had this, in the end, we had this Turing machine Q that while tape I is non-zero, it does M, basically. So now we continue with the following definition, the central, basically, for at least for today and next lectures, is that what do we mean a function is computed by a Turing machine, right? So the definition is straightforward. So always here, by the way, and before also, bin y means, so y is a natural number, so bin y is the binary representation of a natural number y. So it's zeros and ones, basically. So let's say I'm given a function f, so it takes r many variables and outputs one variable, so it's a general r-ary function. A function fm computed by Turing machine m, right? This is what I want to define. So I have this function here, and we say that Turing machine m computes this function. Respectively, I will write f equals fm, meaning that the function computed by machine m is f, is that if you have an r many natural numbers from x1 to xr, so these are r natural numbers, so we will just by convention make our Turing machines work on zeros and ones. So I will say that if my machine m on tape 1, so this is what it means, as an input, it starts on binary representation x1, hashtag binary representation x2, binary representation x3 up to xr. When it's finished working, so I start my machine on this input, it does whatever I programmed it to do, and when it's finished, there's a binary representation of f of x, basically written on tape 1. So this is what it means. So a straightforward definition. This is what is meant by Turing machine computes this function. So for example, if I would have a Turing machine that computes x plus y, this means that when I start my machine with x hashtag y written in binary, it should do the computation and it should output x plus y, whatever this number is, as a binary. We already saw one Turing machine that computes a successor. This was a binary incrementer. So started with a binary number, it outputs that binary number plus 1. So this would be a Turing machine that computes S function. That just a one variable function that increments by 1. But in general, we have R here, so you have R many inputs. And now we say that a function is Turing machine computable if that there exists a Turing machine that computes it. So in most generality, what this means nowadays is a function is Turing machine computable basically means there exists an algorithm that computes this function. And that algorithm for us is by definition something that can be written in deltas of a Turing function. So now we move to our main result, if we finish today, I don't know, that, okay, what functions are Turing computable, meaning for what functions can I write Turing machines for? And the theorem is that all mu-recursive functions are Turing machine computable. This will prove, so there's two sides, so in the end I want to prove that mu-recursive functions are exactly the same as Turing machines. And the one side is that if I have a mu-recursive function, that means I can define it using recursion or composition and constants and successor and so on and so forth, then that means that I can construct the Turing machine that computes it. Basically, this is one side. The other side would be that now let's say I have a function that is computed by an algorithm, meaning a Turing machine, then there exists a way, a derivation in mu-recursive thing, derivation of mu-recursive functions that constructs this. That would actually prove that mu-recursive functions and Turing machines are the same thing in terms of computability power. But first I have to prove this one, so maybe that will be after the break, the second part. But the first part is that if I have a mu-recursive function, it is Turing machine computable. So now the question is the following: how do I prove this? What am I supposed to demonstrate to show that mu-recursive functions are Turing machine computable? Let's actually record this. So what does it mean to prove this? It's the same exact strategy as we did for when we proved that, where was this that we did this? I think when we proved that, when we were constructing NFA for regular languages, remember? How did we prove this? We proved this by, we proved that we can construct an NFA for single letters, and then we proved that, okay, now you can construct for concatenation with epsilon moves, for union, and for things like that, and for Kleene star. And then we said, then it proves the whole thing. The idea is the same here. If I construct a Turing machine that computes constant functions, I construct a Turing machine that computes successor function, which I already did, by the way. And if I construct a Turing machine that computes projections, what else do I have to demonstrate? Let's say I have these three classes of Turing machines that do this. Then I have to show that if I have two things that are Turing machine computable, then their composition, there must exist another Turing machine that computes the composition of these two things. Then I have to show that if I have a Turing machine that computes function blah blah blah, and the other function is defined as a recursion, primitive recursion of previous functions, then this is also Turing computable. And the third one I have to show that, let's say I have a function which is computable by Turing machine, and now I have a new function which is a minimization of this function, then that new function should also be Turing machine computable. So if I prove this, however many things I listed, I will be done. But first what we have to establish is that there exist Turing machines that compute constant functions. What is a Turing machine that computes constant function 7? Let's say a function that takes r many inputs and outputs 7. Yeah, exactly. So this is a Turing machine that is written here. So let's just emphasize one thing. What is this Turing machine? Remember, we constructed a Turing machine on previous slides that erases tape 1. So this Turing machine, this TM that computes constant function rs, should take r many inputs, so there are many inputs, and always output s. This is what it does. So let's say s is 7, so it takes 5 inputs and always outputs 7. Then what I should do, I erase tape 1. This is a Turing machine we already constructed. So it doesn't care what is the input. So it has r many inputs on the tape. It completely erases this input. And then this Turing machine with the semicolon, this is concatenated. We constructed how to concatenate Turing machines with a Turing machine that tape 1 equals binary s. We did this also when we said that you can write any word on the tape. So the word in this case is the binary representation of 7. So what this machine will do, it will erase the tape and write 7. This is exactly a Turing machine that computes constant function 7, because any input you write, it erases it and writes 7. So it's a Turing machine that computes the constant function. What is the Turing machine that computes the function successor? Exactly. The successor function is a Turing computable by regular Turing machine. By the way, the machine we constructed, I don't remember, was it regular? Did it come back all the way to the left? If not, you can make it come back all the way to the left. But a regular Turing machine is the one where when it's finished, it's all the way to the left. But successor function is computed by, this was the name of our Turing function, tape 1 equals tape 1 plus 1. Okay, what is the Turing machine that computes projection? So what this machine is supposed to do, so you give it an input, there's some binary number, hashtag binary number, hashtag binary number. Let's say you give it, it takes 3 inputs. You give it 3 inputs, so you're computing P32. P32 is a function that takes 3 inputs and outputs the second guy. So what this machine is supposed to do, it's supposed to single out the middle guy between hashtags and print it. How will you do this? So it is actually this. Let me show you. So you have projections PIR. So that means it takes R many variables and it singles out the ith variable. So we had this Turing machine, it was in the exercises basically, that what does it do? Let me write it. So we had something like this. So if you have x1 hashtag x2 hashtag and so on up to xn. So let's say this is your input, x1, x2 are just binary numbers. So we had the Turing machine that outputs tail of this thing, whatever is written here. And what is the tail of this guy? This is just x2 hashtag and so on up to hashtag xn. So it just, there's an exercise to write, there was an exercise on your worksheet to write out the Turing machine that just erases this guy. This is very easy. Just in the start state, you keep on erasing until you see hashtag. So this will output the tail. So let's say there's also another Turing machine we discussed. This is head of this thing, and this outputs x1. So you just keep on reading it, and once you see hashtag, you switch into a state when you start erasing or whatever, putting blanks. So then what will be the projection Turing machine? This will be the Turing machine that outputs the tail. So you erase x1 basically. Then you erase, so you concatenate with the machine and you keep on doing this I minus 1 times. So you erase x1, erase x2, erase x3, and now you're at I. And once you're at I, you have xi to xi plus 1, xi plus 3, up to xi plus n. You output head of that tape. So you output xi. So this will be a projection of the ith guy. So it's a very easy thing. So these 3 things are very easy basically. So constants, successor, and projection. Now I have to go into, so let's actually understand what we're doing here. So function composition. So now, I have constants, projections, and successor. So now I'm claiming that if the following functions are computable by Turing machines, I always throw in regular because it's easier, because if you are not really regular, you cannot really compose, because when you start the second Turing machine, the input has to be only on tape 1, all the other tapes should be erased, and you should stand in the beginning of the input. We gave this requirement, so I throw in regular, and all the machines I constructed for this were regular on the previous slides. But anyways, so let's say I have a function f of r many variables and r many functions g of m variables. So what I want to do, I want to plug in this r many g's inside f. And let's say I know that f is Turing machine computable and each of gi's is also Turing machine computable. Then I claim that there exists a Turing machine that plugs in g's into f. So that would mean if, let's say, if x squared is Turing, I know that, let's say, x squared is Turing computable and x plus y is Turing computable, then there is a machine that takes x plus y, plugs it into x squared, and basically computes x plus y squared. This is what I want to prove. This means that now if I have projections, constants, and successor, which are all I showed Turing computable, then I can plug them into each other. It will still be Turing computable. And if I do this for composition, for primitive recursion, and minimization, I'm finished. Okay, how will I do this? How will I construct a new Turing machine from the one Turing machine here and R many Turing machines here. How do I do this? First I have to this is actually unnecessarily tedious, but let's still do it, meaning that how many tapes am I using for this new machine I'm constructing? So for all I, so I have R many G's. So for all I, Gi is computed by, let's say, I don't know how many tapes does Gi need, I just know that it's computable. So let's say it's a Ki tape machine, big Gi. So big Gi is a Turing machine that G1 is the Turing machine that computes small G1. And let's say it uses K1 tapes. I don't know how much is it. And let's say F is computed by K prime Turing machine, big F. So big F computes F, big G's compute each of the G's, and I don't know however many tapes they need. It's Ki's for each G and K prime for F. And now how many tapes am I, so I want to construct something that computes H. H is G plugged into F. So how many tapes does H use? I will take maximum, so K1 to KR, these are finite amount of tapes. It has the biggest number, so let's say 17, I don't know. And I take the biggest number of K's from 1 to R and K prime, and then I add on top of it R. R is however many variables are here. I might as well just say that I use as many tapes as I like. And then we'll see all along the road how much do I need. 10 million tapes. So I have no bound there, but this is exactly the lower bound I will need for the most. So this is the maximum amount of tapes I will need. Whatever the tape is needed to compute F and G, the biggest amount, plus R. Okay, how do I compute this? So what am I supposed to compute? Let's look at it. I'm supposed to compute what? On tape 1, so let's open this up. So on tape 1, I have an input x1 up to xr. So they are all represented in binary, whatever. So I have r many inputs, x1 to xr, separated by hashtags. And actually, there should be m many inputs, right? Maybe there is a mistake. We'll see. So this should be probably m here. So I have m many inputs, and I have to output h evaluated on these inputs. Like this, right? So I have input on tape 1, this should go up to m, up to x1 to xm, let's see. And so what am I doing now? So I have this, imagine these are my tapes. So what am I doing first is, yeah, this should be m. This is a mistake. So this r should be m. So let's recall what am I doing here. So in order to show that my Turing machine computes H, I have to start on an input and give an output of H. So input for H is m many numbers. How do I compute this? I take each number, plug it into G. So I take the G of X, G2 of X, and then compute F of this thing. So first what I will do is I copy tape 1 to tapes 2 to r plus 1 and then erase tape 1. So let's look at the picture here. So let's say, so I had this is up to m, so I had this input here, right? What I did is I copied this to tape 2, you know how to do it. There exists a Turing machine that takes tape 1, copies to tape 2, then I can erase tape 1, and I also copy this thing to tape 3, and there are many, so I do this r many times. Here it is, so I'm copying tape 1 to tape 2 to r plus 1, and then erase tape 1. This can be written this way as a code. This means for I1 to r, tape I plus 1 becomes tape 1. So you're copying tape 1, and then you're concatenating this with erase tape 1. Even though this looks like I'm writing some kind of code, what I'm really writing, these are just Turing machines, which I named them as if they were some codes. So that's it. So this is how it looks like now. In the beginning, I had m many inputs here. Now I have m many inputs or r many tapes, and then everything here is empty. And I do have this many tapes because remember I have r and plus all these things here. So this many tapes are available. What next? So you can understand, I don't know if you get what I'm doing. So now I'm going to compute g's on each one of these things. So I know how to compute g here, g here. These are now inputs for g's and they take m variables, so it should be m here. Now what I'm going to do is for all I from 1 to r, I will compute on tape I plus 1, so starting from 2 to r plus 1, I will compute gix on this. So I apply g to this, and I know that the Turing machine exists that computes g, but it needs maybe, so let's say, so what is happening here to describe it better here. So I have to compute g1 on this, right? But maybe g1 takes, I don't know, k1 tapes. So I'm going to use this tape for g1 and all the tapes below. So I do not want to touch these tapes. So if you think that I have many tapes available here, I apply G1, I compute G1 here just using these tapes, then I compute G2 using these tapes, then G3, and I do it all the way up, down to here. And so it says for all I from 1 to R, compute tape I plus 1, I just compute G, and I use tapes I plus 1, so this tape plus starting from here downwards. And if you think about it, this is exactly however many tapes you will need, because if G uses K3, so you get this point. And for all I to 1, from 1 to K, I compute GI on tapes I plus 1, R plus 2, up to R plus 1 plus K I, whatever. So what will be the result of this? The result of this will be this. This will be the result. That now I have blank here, and then I computed g's all the way up to here. What should be the next step? The next step should be that I should compute now f. So I have this thing here, and now I just compute f. So I compute on tape 1, I concatenate I bring all the g's up here, this binary, the results of g's up here on tape 1. And now tape 1 becomes so how do I do this? How do I copy this? Tape 1 becomes tape 2, I erase tape 2, and for I goes to 1 to K, I do tape 1 becomes tape 1 concatenated with tape 1 plus I, and I erase tape 1 plus I. This is very complicated way to say that from here, I just copy each one of them up here, and I go up to here, and then I just apply F. Which is again Turing. So the compute result by F, and this is finished. Okay, it might seem complicated. I don't know why it looks complicated now that I look, but it's extremely simple what is happening here. Okay, let me explain it, Jordan, what we did. So just this is just to reiterate that all the syntax that we were using is exactly things were constructed here before. So this is this G I plus 1 R plus 2 blah blah blah. This was exactly this Turing machine that was indicating that do exactly what G did, but use the tapes this and this. And the for loop that we're using is just a concatenation of Turing machine that was formally and completely described here. So what I am really saying here that all the syntax that I'm writing, these are actually definitions of Turing machines. This is a Turing machine that concatenates G1, G2, G3, G4, but not just G1, but G1 that is using these tapes instead of the same tapes that G1 would be using first and second and third tape. No, do the same as G1, but instead use the tape 2 and R plus 2, and so that you do not distort the tapes that are needed for the G's that are coming in the future or whatever. So this actually now computes the composition. So next, what we have to do, so this computes composition. Now I have to compute primitive recursion. This is more complicated in the sense that previously it was just very straightforward. Write them down, compute its G, copy to tape 1, compute F. Now, let's say the following functions are computable. So I have a function, so this is the definition of recursion. So I have function G of R variables, which I know the Turing machine exists, function H of R plus 2 variables for which the Turing machine exists, and now I'm saying that I can construct a Turing machine for function F that is defined by primitive recursion. Because we know F, how is F defined? On n plus 1, it uses the previous values of F, n, x, and there's primitive recursive composition of these three things, and on 0 value I can compute it. So now I want to construct, so let me just reiterate one more. So let's try to do this. So again, how many tapes do I need? First I have to establish the number of tapes that I'm using, and let's say this G, for the base case G, is computed by a k-tape Turing machine big G, and let's say H, goes into this recursion here, can be computed by a regular k-prime Turing machine big H. So how many tapes would I need to compute F? I'm claiming that you take the maximum number of k and k prime of machine G and machine H, and you need 3 more tapes. But I might as well take 100 more tapes here, it doesn't really matter, it's all theoretical. But let's say this is the minimum number, so 3 more tapes. And so how should I compute F? Computing F means that if I start my Turing machine with binary number, so it takes how many variables? N plus however long x is. And x is what? R long. So it's r plus 1 variable. So it starts with n, and then you have x1, x2 up to xr. And when you start your machine, it should output whatever f outputs on this input. This is the idea. And how do I do this now? First, so these are my tapes of what I do is tape 2 becomes head of tape 1. This means, so this is written on tape 1. Look. So this is where I start. This is written on tape 1. So tape 2 becomes head of tape 1, means I'm copying this. This is a specific Turing machine. Tape 2 becomes head of tape 1. I'm copying binary n here. Then tape 3, so I'm concatenating this with tape 3 becomes tail of tape 1. So I copied n here and I copied x1 to xr to tape 3. Then tape 1 becomes 0. So I initialize this, I overwrote blanks with 0. Tape 4 becomes tape 3. So tape 4 also becomes this guy here. And then I compute G on tape 4. So G is my base case. So G, this 4 up to k plus 3 means that do not use the things I wrote over, only use tapes below you. So starting from tape 4 up to, that's where the 3 comes from. Because these 3 tapes are already occupied, so G, you're only allowed to use tape 4 and the tapes below you. So in the end, I will have 0 here, n here, x1 to xr here, and gx here. We all agree, right? So what next? Now, this thing does not, yeah, again, let's zoom in. Okay, what next? So I have this situation. So in the following while loop, we change I from 0 to n, and after I passes off the loop, we have the situation on table 5. What I'm doing basically is I'm doing the while loop. I'm incrementing this guy with I. So on the first step, I will increment this by 1. I will decrement this by 1. And I will compute f1x. Because what's written here basically is that 0, n, and here I have f0 written out. So f0x is computed on tape 4, and now I want to compute f1x on tape 4. And for that, I do it, I increment this, I decrement this, and then I compute f1x. But how do I do this? This is what I want to achieve, and this is how I achieve it. Let me first pause and ask. So how is this thing achieved? I hope it. Yep, it works. So how is this achieved? Remember the while loop we constructed on the previous slides that was doing while something is non-zero, do something. So this will go like this. While tape 2 is not 0, meaning initially it's n, it's not 0. So I'm decrementing until I become 0. While tape 2 is not 0, do what? Tape 1 becomes tape 1 plus 1, so I'm incrementing tape 1. Tape 2 becomes tape 2 minus 1, so I'm decrementing tape 2. Tape 4, now this guy here, becomes tape 1 hashtag tape 4, meaning I'm taking this guy here, initially it will be 1. I'm putting it in front of this guy and I'm computing, and then tape 4 is tape 4, tape 3, so basically, so tape 4 becomes tape 1, tape 4, and then tape 4 becomes tape 4, tape 3, so it's not, and then I'm applying F. So let me, oh yeah, I wasn't ready. Initially, when I initialize this whole thing, this is after I iterations. Initially, this says n, this says 0, this says n when I is 0, this says, when let's say I is 0, this says 0, this says n, this says whatever the input is, and what does this say? This is f0x, which is gx. Initially, I just put g there, so this is gx initially. Now, what happens on step 1? On step 1, I increment this, this is 1, this is n minus 1, this is not touched, basically it's the input. And now here, I have something like this. I have 1 concatenated with gx and concatenated here on the step 2 with an input. So on step 1, you have, on this step here, you will have 1 gx input, and then I compute h. So I compute h, which is h is computable by a Turing machine, so I apply h to this, and this exactly will give me f1x. And I repeat this for f2x, f3x, all the way until this is completely 0. Until this guy is decremented to 0, the second tape, and this while loop will exit with tape 2 equals 0. I will have tape 1 will be binary n. As a result, this will become 0, this will become n. And the result that I want to get will be on tape 4. And only thing I have to do is now copy this to tape 1. So tape 1 becomes tape 4, erase tape 2, erase tape 3, and erase tape 4. We're out of time. So you ask questions.